It's really a pleasure to give this presentation. It's been a joy carrying out physics research here at MIT among the physics community. I've immensely enjoyed my time as a Pappalardo Fellow, especially the opportunity to break bread and talk shop with other fellows and physics faculty here in the department. Many thanks to Neil and Jane for this opportunity. And this afternoon, I'll discuss my work in bringing to fruition a new pixel technology which enables neutrino oscillation precision measurements. We start with the standard model of particle physics, which is remarkably robust in the description of the fundamental building blocks and interactions that describe the universe. Although incredibly robust, we know the standard model is incomplete. In particular, neutrinos are described in the standard model as massless, chargeless leptons that interact through the weak force. However, we know from experimental observation that neutrinos are in fact massive. Neutrinos are oddballs in that they have an incredibly small mass, more than 1 million times less massive than the next largest fermion. The mass generation mechanism for neutrinos is unknown, and the value of their mass is unknown. Neutrinos come in 3 flavors or 3 types: the electron neutrino, the muon neutrino, and the tau neutrino, which you can think of as lighter chargeless cousins to the electron, muon, and tau charged leptons. In shorthand, we represent the neutrino by the Greek letter nu, or nu, and refer to neutrino flavors nu-e, nu-mu, and nu-tau. Massive neutrinos are direct evidence of beyond standard model physics, and studying neutrinos may provide insight to a number of outstanding questions, including the matter-antimatter asymmetry in the universe we observe today. From observation of neutrino oscillations, we know 3 flavor states, nu-e, nu-mu, nu-tau, are non-trivial linear combinations of mass states nu-1, nu-2, and nu-3. By careful measurement of these flavor transformations, we can from the different flavors, we can test our understanding of neutrino properties. Specifically, how do they mix? How many are there? And is there an underlying fundamental symmetry governing their transitions? So from my observations in my career in physics thus far, to work at the bleeding edge of the frontiers of particle physics, there are really 3 keys for experimental success. First, you need a clever experimental design to carefully test your hypothesis, and to the extent where you can, dead reckon your observable from confounding factors. Second, it's advantageous to leverage advanced computational techniques, including statistical methods, machine learning, artificial intelligence, to boost sensitivities, signal to background discrimination power, et cetera, when carrying out a physics analysis. And lastly, and this is where my work is focused, to advance detector technologies to enable new high-precision measurements. So today, I'll tell you about my work on the Deep Underground Neutrino Experiment, or DUNE. And what I do on DUNE is I develop and characterize a novel pixel technology. So it's an end-to-end system, starting from bare ASICs as shown on the left. An ASIC is an application-specific integrated circuit, to large anode planes, which are tileable, a large printed circuit board, which features 10,000 individual channels at 3.8 millimeter pixel pitch, is shown in the middle there. And then the corresponding readout electronics to drive analog and digital signals across these electronics, and that's shown on the right. So I work on developing an integrated system such that we could image neutrino interactions at the fine-grained millimeter scale, and also provide calorimetry with those measurements. So before I get to that, let me provide some context as to why this technology is needed and how it will be deployed to make precision neutrino oscillation measurements. So first, the discovery of neutrino oscillation. Art McDonald and Takaaki Kajita were awarded the 2015 Nobel Prize in physics for the discovery of neutrino oscillations, which shows, again, that neutrinos have mass. So when we do this type of neutrino oscillation measurements, what we do is we look for the disappearance of a predominantly muon, for example, neutrino beam over a baseline, or we look for the appearance of one flavor to another. In this example shown on the right, this is from the CAMLAND reactor-based experiment in Japan, where they were measuring electron antineutrinos, and they show here the survival probability of those electron neutrinos as a function of the baseline, the distance which the neutrinos traveled and their energy. And you could see a clear oscillatory behavior, and this is what we're referring to when we mention neutrino oscillations. Specifically, the probability of their survival depends on their baseline and energy, and this oscillates as a function of those two parameters. This story and this endeavor in neutrino oscillation physics actually originated with observation of solar neutrinos back in the early 60s. Back then, we knew that neutrinos are a product of fusion, which powers the sun. And by measuring electron neutrinos emitted from the sun, we could further understand our solar models. So Ray Davis was an experimentalist who carried out a decades-long experiment, carefully measuring electron neutrinos emitted from the fusion cycles in the sun. And John Bacall was a theorist who very meticulously and carefully derived our prediction on solar neutrinos that we should expect to measure at Earth. And for decades, there persisted a stark disagreement between measurement and theory. And this was the so-called solar neutrino problem. And it should be noted that other experiments subsequently came along confirming that we saw a deficit of electron neutrinos relative to the expectation. And of course, the theorist was really put under the gun trying to understand and reconcile the measurements. But in fact, both experimentalists and theorists were correct in this regard, in that the deficit was due to neutrino oscillations. So this experiment is called the Homestake Mine experiment, and took place in Leeds, South Dakota, and we could think of it as the original neutrino oscillation experiment. And the experiment that I work on, the DUNE experiment, actually will be cited in that same underground mine in Leeds, South Dakota. So now I'll tell you about the Deep Underground Neutrino Experiment, or DUNE. It has three main components: broadband, high-intensity neutrino beam that originates on site at Fermilab in Batavia, Illinois. Also at Fermilab is a near detector complex. And these detectors measure the flux composition of that beam before the beam has undergone significant flavor transformation. That beam is shot through the Earth, roughly 800 miles, toward the Sanford Underground Research Facility in Leeds, South Dakota, the same site for which the original solar neutrino measurements were taken. And underground, a mile underground, we have 4 gigantic detectors. So the idea of this experiment is to measure the flavor transformation as a function of distance. And from that, we could really test our understanding of neutrino oscillations and the various physics that they involve. So we start with a predominantly muon flavored beam at Fermilab, and we look for the disappearance of muon-type neutrinos at Sanford. We also look for the appearance of electron-type neutrinos. I should note that this plot, as shown on the bottom here, is fairly representative of the flavor transformation, and you can see that there's a significant tau neutrino contribution. However, we do not have capabilities to directly measure those tau neutrinos, so we infer their presence, but we do not actually measure them. So a little bit about the FAR detector. These are actually 4 gigantic detectors located a mile underground. Excavation of the detector hall was completed over a year ago. The photo on the left is a picture of that cavern during excavation. Over 800,000 tons of rock was removed to create this facility. That's equivalent to 8 aircraft carriers in mass, so a very immense amount of rock. And in these very large caverns, we'll put gigantic detectors. These detectors have liquid argon as the active target, and they're the size essentially of skyscrapers. And they're so large because neutrinos very rarely interact, and for the vast majority of time, there's not much going on in these detectors because they're underground, they're shielded from cosmic rays. We only expect roughly 30 neutrino interactions per week in 40 kilotons of detector material. This is what our signals look like. You could see various topologies. The color scale here represents the ionization deposition or the energy scale of that particle. And so this is a fine tracking detector with calorimetry represented by the colors. And we could see the clear topologies of the particle tracks. I should note that we don't see the neutrino. The neutrino is chargeless, but we infer its presence through its interaction with an argon nucleus, and we measure the products of that interaction. So this particular interaction is a muon neutrino charge current interaction. We know that because we can identify the long muon track. And then we measure by calorimetry the other final state particles in this interaction. And through machine learning and advanced reconstruction techniques, we can resolve the neutrino energy by making these measurements. We contrast this with this type of topology, where you see a spray-like shower topology. This is an electron neutrino final state. And we, of course, want to measure the appearance of these type of signals and the disappearance of these type of signals relative to the measurements that we make at the near detector. So going back to the Fermilab site, the beam originates at Fermilab through the acceleration of protons through a linear accelerator, a booster ring, and then those protons impinge on a target. They produce hadrons. Those hadrons are focused through a pulsed magnetic horn. And in doing so, we can sign select preferentially hadrons of one charge or another, such that we could create a predominantly neutrino beam or a predominantly anti-neutrino beam, majority of muon-type neutrinos. So we have this very broad band, high energy beam, mean energy roughly 2.5 GeV, and we point that down through the Earth towards South Dakota. And on site, we have a near detector where we measure the flux composition of that beam. And this is where I come in. I showed you the fairly simple topologies and quiet event that we measure at the far detector. The situation is vastly different at the near detector. At the near detector, we actually observe a beam neutrino pileup. Given how intense the beam is, we have roughly 50 neutrino interactions per 10 microsecond instantiation of the beam. This is an absolutely unprecedented experimental regime for a neutrino experiment to operate. So because of this, we need to push forward our technology such that we could actually read out these signals. And here I'll explain why. Historically, we've read out these liquid argon detectors with so-called projective readout. When you have a liquid argon detector, when a charged particle traverses the active medium, it ionizes the argon-producing ionization electrons. we bias one side of the detector and keep the other side, the anode, at ground, such that we create a uniform electric field. Those ionization electrons drift to the anode plane, where we typically have multiple planes actually in parallel with wires or strips at various angles of inclination, such that on a given plane, we can create a 2D picture in time and channel of the topology of interaction that occurred in the active volume. By combining the various planes, we can create a 3D image. And that's how we historically have read out these detectors. However, given the very high occupancy, busy environment of the near detector, there's ambiguity in our 2D images such that we can't faithfully reconstruct to 3D. So that's motivated the development of 3D true pixel readout detector technology, for which I work on, for which we inherently produce a 3D image in the raw native data. So we've brought this to fruition through the so-called LARPix concept. I show some LARPix chips or ASICs on the right. The idea is the following. Each chip can actually is connected to 64 individual detectors. So this little chip is actually a system, a detector system on a chip, where one channel has a pixel sensor that it's connected to. When we induce current on that pixel due to the arrival of ionization electrons toward the anode plane, we induce a current. That current is then converted to a voltage. We compare that voltage to the preset discriminator threshold on that channel, or if the charge on the pixel exceeds the channel threshold, we initiate a trigger logic. And then we have an ADC to convert that charge to some digitized bit. That digitized bit is fed to the digital back end of the chip, where it is serial read out of the system through a complex digital logic that I'll not discuss. But that's the basic idea on how we pixelize these large anode areas. And the key is to do it with low power dissipation, to do it at cryogenic temperatures, given that these sensors are in liquid argon, and to digitally multiplex thousands, tens of thousands, millions of channels out of our detector. And that's what we've done. And we've created an end-to-end charge readout system, which includes the ASICs, large format printed circuit boards, which are the actual anode planes in our detector. These circuit boards are tileable such that we could instrument any area of any dimension. And then we have cryogenic cables connecting to the outside world. So those feed the signals to our warm electronics. And those warm electronics are connected via Ethernet to our data acquisition computers. As shown on the left is the raw data that we read out of our detector. You could see that it's just natively 3D. There's no massaging going on at all for the data. There's no noise filtering or signal processing. It's just inherently sparse 3D images where each point is an individual trigger of a pixel channel. And each point has obviously spatial information as well as some charge information as provided by the ADC data work. So coming back to the DUNE experiment, yes, it's very nice to have a pixelated charge readout system, but what are you comparing it against? How well do you need to do? So for the DUNE experiment, we're making high precision spectral measurements of the neutrinos at the FAR detector. So an example of electron neutrinos measured at the FAR detector after, for example, 3.5 years running in neutrino mode for the beam. The spectrum is shown on the right. And you could see that we expect order 1,000 events or so. And in terms of the physics that we want to pull out, I need to have reliable uncertainties on each data point such that I could differentiate various physics parameters of interest. Specifically, I go from observed neutrino events as a function of neutrino energy, and I infer neutrino oscillation probability as shown on the right, excuse me, as shown on the bottom. And from that, I can pull out the physics of interest by these inferred subtleties in the spectrum shape. So to do this reliably, I need to provide a measurement with small systematic uncertainty. At these statistics, we're no longer statistics constrained, but really we have to be mindful of our systematic uncertainty budget. For DUNE, we're trying to keep the total systematic uncertainty to less than 2%. So the near detector plays a pivotal role in this systematic uncertainty. Specifically, we need to make an accurate prediction of the measurement of the far detector measurement, and that is done by carefully measuring the neutrino flux at the near detector and the various final states, the modeling that goes into how neutrinos interact with the argon medium. So overall, the near detector performance must exceed the far detector performance. So in producing this charge readout system, we'll begin production of it in 2027, and it'll actually be deployed in 2031. So between now and then, we need to make sure we get it right and that our design is performant and will deliver. So to do that, we prototype. So an example of some of our large-scale prototypes is a 2.5-ton optically segmented liquid argon TPC that was deployed at Fermilab and operated for roughly 4.5 days in a NUMMI neutrino beam. This is detectors at roughly 60% scale of that which we'll deploy at DUNE. This detector had over 400,000 channels at 4 millimeter pixel pitch. We observed no serious detector pathologies, but there are several features in the data that needed to be understood. So I should note that this is older technology, and we've since, through great efforts, has characterized and understand the underlying mechanism from each feature and improved our system, be it in simulation, calibration, hardware itself, or software filtering to mitigate or totally remove these effects. In our latest generation system, operated in November last year, we've largely removed or mitigated all of these effects. And this is a larger system to scale, and we're very happy with the imaging performance there. I should note that this is a technology that's not only enabling for the near detector, but potential applications at the far detector as well, specifically in nuclear astrophysics searches, for example, of our friend solar neutrinos, detection of supernova burst neutrinos, proton decay, so on and so forth. So it may be possible in the future to deploy this readout technology at the unique environment of the far detector. And we want to do that because this detector provides a continuous readout independent of triggering signals sent or needed from other subdetectors. And we could do this with individual channel thresholds at the 200 keV level. So in conclusion, I work on a enabling technology for measuring a neutrino oscillation physics. This is beyond the standard model measurements. I've implemented a low-power, crowd-compatible performant pixel readout technology that's required for the DUNE physics objectives. MIT is among many institutions leading this detector development, and we look forward to exciting data ahead. And in closing, I want to thank Neil and Jane for this incredible opportunity. It's wonderful to be part of the MIT physics environment, and it's also been wonderful getting to know the two of you. So thank you very much.